Okay, before we start multiplying and dividing numbers with scientific notation, let's just look at a sad example of how we can convert a number into scientific notation. This is our national debt. Okay, it's changing so fast that I had to just guess at these bottom numbers, but it increases at somewhere between $30,000 and $40,000 every second. Okay, but what is this number? It's $23,745,197,241.63. That's a clunky number. Let's put that into scientific notation, shall we? We're going to take this decimal, we're going to move it all the way back between the 2 and the 3, and we're going to round it off somewhere. 2.3, let's just go one more digit and call it 5. Times 10 to some exponent. Well, how many decimal points did I shift it there? 3, 6, 9, 12, 13 places. Okay? That's a more concise way to write that number. Okay, now if I multiply this out though and go back to standard notation, I've lost all this precision, right? Because all these are going to be 11 zeros after it here. Okay, and if I go back and fill in my commas, I've got 23,500,000,000. That's it. That's rounded off. Okay? We've lost significance, but again, when you're talking 23 trillion, the thousands, 10,000, 100,000s, millions, 10 millions, 100 millions, even up in here into the billions. Sorry, I'm 3 places off, but even up here into the billions, it's chump change. It's nothing compared to 23 trillion. Okay, so yeah, we lost some significance, but we got the bulk of it. We got the big number, $23,500,000,000,000. Okay, we don't care about the little millions and hundreds of thousands. That's nothing. That's pocket change. Okay? All right. That's a big number. So go to this website if you ever want to just see how money is being, whatever, how much money is being spent. But that's how we would write the national debt in scientific notation. Okay, let's talk about multiplying numbers in this notation. So now I'm on example 5 on page 245. If I have two numbers both in scientific notation, so I've got 4 times 10 to the second power times 2 times 10 to the third power. It's real easy. I'm going to multiply those two numbers before my powers of 10. So 4 times 2 is 8. And I'm going to multiply my 2 powers of 10. And I know how to do that. 2 squared times 2 cubed. I add the exponents. And I get 2 to the 5th power. Okay? So 8 times 2 to the power 5. Sometimes it's not quite that simple. I might have to make a little correction. And if you look at part B, I've got 3.7 times 10 to the third power times 2.5 times 10 to the negative 1 power. So first I'm going to multiply the 3.7 and the 2.5 together. And when I do that, I get 9.25, so we're still going to be okay as far as corrections go. Times some exponent. Now I've got 10 to the third times 10 to the negative 1, so I'm going to add those together and get 10 to the second power. Okay, so far so good. C is where we're going to have to do a little extra, because I've got 8.4 times 10 to the negative 2 power. And I'm going to multiply that by 5.2 times 10 to the negative 3 power. And when I multiply the 8.4 and the 5.2, I get 43.68. And when I multiply my powers of 10 there, 10 to the negative 2 times 10 to the negative 3, I add the exponents together, and I'm going to get 10 to the negative 5. Okay, but the problem here is that I'm not in the correct notation, because I'm only supposed to have one number and then a decimal point, but you see I've got the 43 and then the decimal point. So I need to make a correction. So I'm going to take that 43.68, and instead of calling it 43.68, I'll call it 4.368 times 10 to the power of 1, because then that's the same thing as 43.68. But then I already had a 10 to the power of negative 5 there, so I have to put that there and then consolidate these powers of 10. So it'll be 4.368 times 10 to the negative 4th power. Okay, all good there? Division's very similar, except instead of multiplying, we're dividing, so we got to remember our rules of exponents for division. All right? If you look at example 6, I've got 3 times 10 to the power of 5, and I'm going to divide that by 2 times 10 to the power of 2. All right, 3 divided by 2, that's 1.5. 10 to the 5th divided by 10 to the 2nd. Remember, when we're dividing, we subtract those exponents. So it's times 10 to the 3rd power. All right, part B. 1.44 times 10 to the negative 3rd divided by 6 times 10 to the negative 5th. So we got some negatives to watch out for when we do that subtraction, but first things first, let's take that 1.44 and divide by 6. And when we do that, we get 0.24. And now let's watch out for that. Let me write that out. I've got 10 to the negative 3rd power divided by 10 to the negative 5th power. So that means off to the side here, I'm going to have to take negative 3 minus negative 5. So that's going to become a plus positive 5. So it's going to be 10 to the positive 2 power. Okay? So watch out for that one. So 10 to the positive 2 power. But we got a problem though. We're not in the right notation because that decimal needs to be on the other side of the 2. So to make that correction, I'm going to call that 2.4 times 10 to the negative 1 power, because that would have turned it into 0.24. But then I already had a times 10 to the 2 power. So this whole thing simplifies into 2.4 times 10 to the 1st power. Okay? That was part B of example 6. All right, what about part C? Numbers are getting a little bigger here. That doesn't scare us. We've got 9.6 times 10 to the 29th power divided by 3.2 times 10 to the 111th power. Okay. The division of those two numbers in the front, that's just regular old division. We'll see what we get. In this case, we get a nice pretty 3, so that's easy. I'm going to subtract those exponents. I need to take 29 and subtract 111 from it, so I'm going to get a negative 82 when I do that. So 3 times 10 to the negative 82 power, 82nd power. Okay. And finally D, 1.25 times 10 to the 3rd power divided by 5. Now that's a little odd, right? It's not a standard scientific notation divided by a scientific notation. Okay, we can make ourselves feel a little better by putting it in that form. We can call that 5 times 10 to the 0 power. Now it's in that form. It's one of those times when that 10 to the 0 might come in handy, otherwise it doesn't help us too much. Now it's regular old division here. 1.25 divided by 5 gives us 0.25, so we're going to need to make a correction here. This is just going to be 3 minus 0. It'll still be 10 to the 3rd power. Okay, but I need to make that correction. So I'm going to call it 2.5 times 10 to the negative 1 power, and then times 10 to the 3rd power. Okay, where did I get from here to here? That decimal, I want it to be there, so I have to multiply by 10 to the negative 1 to make it equivalent. So it becomes 2.5 times 10 to the, I'm adding those two exponents, 2nd power. Okay? All right. That was example 6. Okay, there's some examples coming up, some word problems, and I have a word problem I always like to do with my classes, and it lets us see what's going to happen on our calculator when we start going into this world of big numbers on the calculator. Okay, now by the way, if we're wondering how to put a number like that into the calculator, you know, that's just an exponent. So you would say 9.6, for example, times 10, and then your exponent button, you know, is probably a button like that to the 29th power. Something like that, okay? If we were doing this whole problem, the safest bet would be to put it in a parentheses and then hit your division sign and put the other one in a parentheses also. 3.2 times 10, exponent button, 111. That's your safest bet. Right, but what happens when we start crunching these really big numbers and we get a number that's you know, we run out of room on the calculator screen, in other words. And what does the calculator do? Well, the calculator goes into scientific notation. Now let's take a look at what that is. So I got a fun little example. Pardon me as I reach for my calculator. I've got a fun little example that also will let us talk about units. Okay, we've done a lot of unit conversions lately, and this is a great problem with unit conversions. So what I always like to do on this problem is I like to calculate something. I want to know how many miles across the observable universe is. Okay, now we need to have a little background information to have a clue, but you know, if the experts say that what we can observe, what we know about the universe is that it is 93 billion, so that's thousand, that's million, that's billion, 93 billion light years across. Okay? Light years across. A light year is not a measurement of time. It's a measurement of distance. Okay? That's not a Toy Story character either. A light year is a measurement of distance. It's how far light can travel in 1 year's time. That's a light year. Okay, so if we know the speed of light, we can calculate how many miles a light year is, and then we can figure out how many miles 93 billion light years is. So we do need one more piece of information that you may not have at your fingertips, and that's the speed of light. Okay, and that speed of light is 186,000 miles per second. Okay? That's fast. Think about that. In 1 second's time, light can travel 186,000 miles. Okay, I think that equates to something like light can travel all the way around the Earth. I think it's 7.5 times in 1 second, something like that. That's fast. Okay, and even at that ridiculously fast speed, it will take 93 billion years to go across the observable universe. Okay, we don't even know what's beyond that. All right, so that's crazy. These numbers are just mind-boggling. Okay, let's turn that into miles. How many miles is that? Well, I don't know. Let me take that speed of light. I know it travels at 186,000 miles per second. Okay, and I know sometimes I'm going to write out the units a little differently than we just did in the conversion section, like MI for miles, but I usually write it out, okay? I'm going to convert this. Just using unit conversions, I know. I want to turn miles per second into miles per year. I don't know how many seconds are in a year. Yes, we could just ask the magic box the question, how many seconds are in a year, and get the answer, but let's figure it out. I know there's 60 seconds in a minute, right? So I'm going to use that unit conversion, 60 seconds in a minute. I want the seconds to disappear, so 60 seconds over 1 minute. And if I do that, you see my seconds cancel, And now I've got miles per minute. I know there's 60 minutes per hour. So now my minutes cancel, and I've got miles per hour. I know there's 24 hours in a day. So my hours cancel, and now I'm going to have miles per day. And let's forget about leap years, even though this is one. There's 365 days in a year. So my days cancel, and if I multiply all those numbers, I'm going to get how many miles light can travel per year, just 1 year. So now I'm going to multiply by 93 billion years. Okay, now you got to bear with me. I got units. I've dropped down to the second line. So this is a numerator and that's a denominator. So the years cancel. And the only unit left on the board is miles, and that's what I'm trying to find. Miles. All right. Let's crunch all these numbers and see what happened. Let me see if you can see my calculator. Yeah, it looks like we can. So 186,000 times 60 times 60 again times 24 times 365 times 93,000 million billion equals, I can't read it, 5.45 times 10 to the 24th power. I think I multiplied by one extra zero in there. I think it should be 10 to the 23rd. Pardon me, let's try that again. 186,000. I think I had an extra zero in that 186,000 because I think I hit it 4 times. Times 60. You know, making videos is no fun because you can't just redo them easily. So I'm moving on with the mistake. Times 60 again, times 24, times 365 equals, oh, and then times 93 billion. There we go. 5.455 times 10 to the 23rd power, and that's miles. Okay, so that's how far across the observable universe is. And see what my calculator did. It stuck a little times 10 to the 23rd. You can just barely see the times 10 there. Let's see, am I sophisticated enough to zoom this? Look at that. Get in there. Yeah, now it's out of focus. There we go. See the little 10 there? Times 10 to the 23rd. Yours may be a little different. Yours may just stick a little 23 up in the corner. You may have a capital letter E and then a 23 after it. That's another way it's done. There's various ways, but one way or another you should have a little 23 in there, and that's what it's talking about. The exponent of 23 in scientific notation. Okay, so a fun little example, not only to get a big number in the calculator, but to practice all those unit conversions. I had to know the speed of light, which I just knew anyway, and then I had to look up this light years across the universe, but everything else was common stuff I knew how to convert, so I could figure it out. Okay, all right, we'll do some more examples in the next video.